It is 7:05 p.m. on July 17th, 1981, and inside the atrium of the Hyatt Regency Hotel in Kansas City, Missouri, 1,200 people are dancing. Above their heads, 3 walkways stretch across the open lobby like glass and concrete bridges, suspended from the ceiling by a handful of steel rods. Nobody looking up tonight can see the flaw. It is hidden inside a connection the size of a fist, buried in a box beam 60 feet above the dance floor. 9 months earlier, an engineer changed one detail on a drawing. He did not know it. His supervisors did not know it. The fabricator who requested the change did not know it either. In the next 4 seconds, that single unnoticed change is going to kill more people than any building collapse in American history. This is the story of how a walkway built to hold dancing couples was, from the day it opened, only strong enough to hold itself up. Now rewind to the beginning. Kansas City, Missouri, in the late 1970s, was rebuilding itself. Hallmark Cards, the greeting card giant headquartered downtown, had poured money into a massive urban renewal project called Crown Center, a cluster of offices, shops, and hotels meant to revive a struggling stretch of the city. The centerpiece was the Hyatt Regency Hotel, a 40-story tower with a feature that architects loved and that Hyatt itself had made a signature of its brand nationwide. A soaring open atrium lobby, crossed by walkways that let guests admire the space from above instead of hiding behind hallway walls. Construction began in 1978. The design called for 3 walkways on the 2nd, 3rd, and 4th floors, connecting the hotel's function block to its guest tower. The 2nd and 4th floor walkways were stacked directly on top of one another, hanging from the same set of steel rods that ran up into the atrium roof. The 3rd floor walkway was offset to one side, hanging independently. It looked elegant, it looked expensive, and it looked to every guest who ever walked across it completely solid. The hotel opened on July 1st, 1980, a year and 16 days before the collapse. Almost immediately, it became a Kansas City institution. On Friday evenings, the atrium hosted tea dances, big band music, and cash bars that drew hundreds of young professionals into the lobby to dance, drink, and watch from the walkways above. It was, by every account, one of the most popular new gathering spots in the city. But before the hotel ever opened, something had already gone wrong. During construction in October 1979, a large section of the atrium roof caved in when a connecting device failed under the weight of workers pouring concrete. Nobody died. The project was delayed for months while the roof was rebuilt. And here is the detail almost nobody in that dance crowd on the atrium floor tonight will ever learn. The same engineering firm responsible for approving the roof also approved the walkway connections. They inspected the roof failure. They did not go back and recheck the walkways hanging beneath it. That decision, or rather that failure to make a decision, would matter more than anyone realized. Because somewhere in a stack of shop drawings passed between a steel fabricator and a structural engineering office, one connection detail had already been altered. Nobody flagged it. Nobody stress tested it. It simply moved through the approval chain like every other page in the set. We'll come back to exactly what changed. For now, remember only this. The walkways that 1,000 people would one day dance beneath were never built exactly the way the original engineers had drawn them. To understand how this happened, you have to understand a single, almost boring engineering decision. The original design, drawn by the structural engineering firm Jack D. Gillum and Associates and stamped by engineer Daniel M. Duncan, called for a continuous steel rod running from the atrium ceiling, straight down through the 4th floor walkway, and continuing down to the 2nd floor walkway. One rod, 2 walkways, threaded with nuts at each level to hold the box beams in place. At this point, the design was already weaker than it should have been. Later testing would show that even this original continuous rod version could only support about 60% of the load required by Kansas City's building code. It was a flawed drawing, but it was survivable. It was never built. The steel fabricator responsible for supplying the rods, a company called Haven Steel, looked at the continuous rod design and saw a construction nightmare. Threading a rod for its entire length, more than 40 feet, so that nuts could be screwed on at 2 different levels, was awkward and expensive to manufacture. So Havens proposed a change. Instead of one long rod running through both walkways, used 2 separate shorter rods. The upper rod would run from the ceiling down to the 4th floor walkway, as before. But the lower rod, instead of continuing up to the ceiling, would now be anchored to the bottom of the 4th floor walkway's own box beam and hang down from there to support the 2nd floor walkway. On paper, it looked like a simplification. In physics, it was a catastrophe. Under the original design, the box beam connection on the 4th floor only had to support the weight of the 4th floor walkway itself, because the 2nd floor walkway's load traveled straight up the continuous rod to the ceiling. Under the new design, that same 4th floor connection now had to support the weight of both walkways at once. The 4th floor's own load, plus the entire 2nd floor walkway hanging beneath it. The load on that single connection had just doubled. At this point, the disaster was still avoidable. The change went through a formal review. Shop drawings were submitted, engineers at Gillum and Associates reviewed and stamped them, but the calculations for the new box beam connection were never independently redone to confirm it could handle double the load. Investigators would later determine the review was cursory, treated as a routine fabrication detail rather than a structural redesign. So the drawings were approved, so the steel was fabricated, so the walkways went up. Here is the number that should stop you. The National Bureau of Standards, which investigated the collapse, calculated that the as-built connection could support only 31% of the minimum load required by code. Not 70%, not 50, 31. The walkway did not fail because of some rare extreme overload on the night of the dance. It failed because from the moment construction finished, it had almost no safety margin left at all. It was, in the words of investigators, carrying virtually no capacity to resist additional loads imposed by people. And there was one more missed chance. Remember that roof collapse during construction back in October 1979? The engineering firm inspected the roof failure and cleared the building to continue. They never went back to examine the walkway connections hanging in that same atrium. Connections fabricated by the very same shortcuts under review. It was the second warning the building gave. Nobody was listening for it. There was a third factor, quieter, but just as important. During construction, Gillum and Associates had asked, on 3 separate occasions, to place a full-time engineer on site to inspect the steelwork as it went up. Crown Center Redevelopment Corporation, the Hallmark subsidiary managing the project, denied each request, citing cost. So the connections that would one day hold 1,600 dancing guests went up with no independent structural eyes watching them. For 9 months after the hotel opened, thousands of guests walked across those walkways every single day. Housekeeping carts rolled over them. Wedding parties posed for photographs on them. Nothing happened. The margin was thin, but it held because ordinary foot traffic never came close to testing its limit. What the walkways could not survive was a crowd. And on the evening of July 17, 1981, a crowd is exactly what they got. Friday, July 17, 1981. The Hyatt Regency atrium is packed for the weekly tea dance. Estimates put the crowd at 1,600 people. Some sources say closer to 2,000. A live band plays. Couples move across the lobby floor. Above them, dozens of spectators lean on the railings of all three walkways to watch the dancing from overhead. Roughly 40 people stand on the second-floor walkway. Another 16 to 20 are gathered on the fourth-floor walkway, directly above it. Remember, this entire structure depends on a single steel connection, sized to carry less than a third of the load it was ever supposed to hold. Every person leaning on that fourth-floor railing is adding weight to a joint that was already failing before they arrived. At 7:05 p.m., witnesses hear a sharp cracking sound, then a series of popping noises like gunshots coming from above. Diners, 42 floors up in the hotel's revolving restaurant, would later say it felt like an explosion rolling through the building. The fourth-floor walkway drops several inches. It pauses. For one instant, it seems to hold. Then, the connections give way completely, and the entire fourth-floor walkway, more than 100 feet long, tears free from the ceiling and crashes straight down onto the second-floor walkway beneath it. The impact is too much. The second-floor walkway's own connections fail in the same instant. Both structures, concrete, steel, and glass, weighing many tons combined, fall the remaining 2 stories directly onto the crowded atrium floor. Imagine standing on that lobby floor mid-song and the ceiling itself comes down on top of you. There is no warning beyond the cracking sound seconds before. People dancing directly beneath the walkways have no time to move. Water pipes running through the collapsed structure rupture on impact. Because those pipes were connected to rooftop tanks rather than the city supply, there is no way to simply shut a valve somewhere and stop the flow. Water begins pouring into the wreckage, rising around victims who are already pinned beneath tons of concrete and twisted steel. For those trapped and conscious, the new terror is drowning before rescuers can reach them. The response is immediate. Off-duty doctors and nurses who happen to be in the crowd, along with hotel staff, begin pulling survivors from the debris within minutes, long before official rescue crews arrive. Kansas City's emergency medical director, Joseph Weckerl, takes charge of what becomes a 14-hour rescue operation. Heavy cranes are eventually brought in because sections of collapsed walkway are too massive to move by hand. In some cases, rescuers make the decision to amputate limbs on site to free victims who cannot otherwise be extracted from the wreckage in time. By the time the search ends, the toll is the worst of any building collapse in United States history. 114 people dead, more than 200 injured. The third-floor walkway, offset to the side and structurally independent of the other 2, is the only one left standing. It becomes almost immediately an eerie photograph. A single bridge suspended in an otherwise empty atrium, hanging over a lobby floor covered in rubble. What killed these people was not a bomb, a fire, or a structural miracle gone wrong. It was 2 rods and a nut, engineered on paper to carry a load they never had a chance of holding. The public did not know that yet. The people who did know were about to face the hardest part of the story, proving it. Within hours, the National Bureau of Standards, the federal government's chief metrology and materials science agency, was called in to determine exactly why 2 walkways built to hold hundreds of people had failed under an ordinary Friday night crowd. Investigators pulled the box beams from the wreckage and found something strange. At several of the failed connections, the steel nuts had not simply sheared off. They had pulled straight through the box beam itself, tearing a ragged hole through solid steel as if the beam had been made of cardboard. That told engineers the failure was not a random defect in one bad piece of steel. It was systemic. Every connection along that beam had been carrying more load than the metal could bear. And here is where the story took a turn nobody expected. Investigators, and later a team of reporters at the Kansas City Star working independently, went looking for a single, dramatic manufacturing flaw. A cracked weld, a bad batch of steel, a construction crew that skipped a step. That is usually what disasters look like. But that is not what they found. The welds tested fine. The steel met specification. The workers who assembled it had built exactly what the approved drawings told them to build. The flaw was not in how the walkways were constructed. The flaw was in the design itself, buried inside a shop drawing change that had been reviewed, approved, and stamped by professional engineers who never reran the math. This is the reveal the entire investigation had been circling. The switch from one continuous rod to two separate rods, made months earlier by the steel fabricator for the simple, unglamorous reason that threading one long rod was inconvenient to manufacture. That single practical shortcut doubled the load on the fourth floor connection. The Kansas City Star's own reporters figured out the mechanics of this flaw within days of the collapse, sketching the same diagram investigators would later publish in the official federal report. One journalist later said the error was simple enough that a first-year engineering student should have caught it on sight, and yet it passed through a professional engineering office without a second look. The Bureau's final numbers were stark. The connection, as originally designed with a single continuous rod, could carry only about 60% of the code-required load. The connection, as actually built, with the split rod design, could carry just 31%. From the day the hotel opened, that walkway was never legally safe to stand on, let alone dance beneath, even with nobody touching the railings. The consequences for the engineers came slowly. In 1984, the Missouri Board of Architects, professional engineers, and land surveyors filed formal charges against structural engineer Daniel Duncan, engineer of record Jack Gillum, and their firm, GCE International, alleging gross negligence, misconduct, and unprofessional conduct. In November 1985, the board found them guilty. Duncan and Gillum lost their licenses to practice engineering in Missouri. No criminal charges were ever filed. A review found no evidence of intentional wrongdoing, only a catastrophic failure to verify a change that looked routine on paper. Civil settlements to victims and families would eventually total roughly $140 million. The men who signed off on that drawing were not careless in any way that stood out at the time. They were professionals, working inside a system that trusted a fabricator's shop drawing to be reviewed the same way a minor detail is reviewed, not the way a structural redesign is reviewed. That is what made it so dangerous. It did not look like the kind of decision that kills people. It looks like paperwork. The Hyatt Regency reopened on October 1, 1981, less than 3 months after the collapse. The atrium was rebuilt. The second-floor walkway was replaced with one supported from the ground by columns instead of hanging rods, and the fourth-floor walkway was removed entirely, never rebuilt. Only the original third-floor walkway, the one that survived, remained. The renovation cost roughly $5 million, and local officials later called the rebuilt structure possibly the safest building in the country. Other Hyatt hotels quietly stopped hosting tea dances in their atriums altogether, but the deeper change happened inside the engineering profession itself. In the wake of the collapse, the American Society of Civil Engineers adopted new guidelines, making clear that structural engineers of record, not fabricators, bear ultimate responsibility for reviewing any shop drawing change that affects a structure's load path, no matter how minor it looks. Engineering schools across the country began teaching the Hyatt Regency collapse as a foundational case study, not primarily as a lesson in materials science, but as a lesson in professional ethics and process. It remains, decades later, one of the most taught engineering failures in American classrooms, precisely because the physics were simple and the human failure was so easy to imagine happening again. Every time an engineer today insists on rechecking the math after a construction detail changes, even a detail that seems purely practical, that habit exists partly because of what happened in that Kansas City lobby. Every building code clause that requires a licensed structural engineer to personally review, not just receive, a fabricator's shop drawings traces its lineage back to a single afternoon in 1981 when nobody did. 114 people died, and 200 more were injured. Not because of a bomb, not because of a natural disaster, and not because of a single reckless decision made in a moment of pressure. They died because a shortcut that looked reasonable on a piece of paper was never tested against the weight of the people who would one day stand beneath it. The gap between what a drawing shows and what a building can actually hold is not always visible. Sometimes it only becomes visible once on a Friday evening, with a room full of people who trusted the floor above their heads. Somewhere, right now, another catastrophe is waiting inside a detail this small. Subscribe to see the next one before it happens to someone else.